Alright, welcome everybody. This is my week 4 video on muscles. So, I have previously filmed this video twice, and both times they haven't saved. So, I'm going to keep a couple drawings from last time, um, just, just in case it doesn't work again. But anyways, we're going to be talking about muscles. So, this is supposed to be a bicep, not a very good drawing. Yeah, we're missing a thumb. There we go. That's a bad thumb. Anyways, muscles are fibers. They're formed into fibers. They're kind of like hair-like structures that they're just built up. And so this picture, what this depicts is this is a muscle that is it's kind of cut at the diameter so you can look and see that hair-like structure, head on as it's coming towards you. It's kind of like looking down a spaghetti noodle. But anyways, so this is our muscle. And this muscle, all of these fibers that make it up, this is what we call a fascicle. I'm sorry. And from the fascicle, this is what we call a sarcolemma. And these are actin and myosin, which make up the sarcolemma and the parts of it. This is called a sarcomere. And so this right here, that is our H line, and this is our Z line. Z disc, I'm sorry. Z line, Z disc. Okay, so our parts of our fascicle, this is our perimysium. This is our endomysium. Okay, and that's just to kind of get a little bit of a insight into what we're doing. Now we're going to be talking about this the sarcomere. So the sarcomere, as we depicted, has the Z disc. So I'm going to be drawing that in red. Draw it pretty big. And then we have these structures coming out here. And these are called a nebulin. And then we have these, draw them as these triangles. These are called titans. And titans are connected to the myosin. Kind of drew them off. There we go. And these myosin, they have these little arms coming out. You can call them arms, you can call them balloons. We actually refer to them as heavy chains. But they are vital in the contraction of muscles. And in the middle, we actually don't have any. And so this is actually we call this the H line, because there's none of those. So as you kind of look here, so a muscle is striated. Skeletal muscle is anyways, meaning it's kind of has like tiger stripes or zebra stripes. And that is just because you have that high density parts of the myosin on the one side, and then in the H line there isn't any. So it kind of makes a little bit of a pattern. We're going to draw one of these nebulins coming out. These nebulins have these circle-like structures on them. And these are called G-actin. Many G-actin are called an F-actin. And they have an affinity. They want to bind with myosin. I apologize, I cannot spell. Okay. And already bound to them are these lines, and we call this tropomyosin. And what sits on top of this is something else called troponin. Troponin. All right. This troponin, we have three different ones. We have a T, an I, and a C. T wants to bind with tropomyosin. I wants to bind with myosin. Sorry, it's not myosin. It is actin. It wants to bind with actin. Silly me. And then this last one here, C, wants to bind with calcium. So there's 4 binding sites for calcium. And 2 are high affinity. And 2 are low affinity. And so what actually happens, so this calcium binding site, that's very vital. So when this calcium is bound to, it actually goes through a conformational shift and opens up like that. What that does is that allows room for these myosin heavy chains, these arms to come in and bind. And so that's how muscles will contract, is where it's filled with these. So as it binds, it works its way tighter, comes in closer, and that's how it contracts. So we have these heavy chains. I'll draw them. They're kind of cross over a little bit, and then they have these big ends on them. The binding sites right there. And so that is how they are connected. What we're going to talk about now, we're going to talk about synapses and how they are associated with this. So we talked about this a little bit last week. The synaptic cleft. This is an area we call a T, call it a circle, T tubule. There's a little bit of calcium in here. We have this area inside. We call the SR. That is sacroplasmic reticulum. We have this thing going on. Copy it down here, make it a little smaller. There we go. Okay, we learned this last week, that in the synaptic cleft we have voltage-gated calcium channels, we have voltage-gated sodium, and voltage-gated potassium. Still here in this T-tubule, we have some more voltage-gated channels. And here in this synaptic cleft, once again, we have this acetylcholine found in these little vesicles. And as they make their way out, they're here, and there's a bunch of receptors for it. And once those receptors bind, there is a chemical shift. And acetylcholine esterase comes and eats the rest of the esterase, or the rest of the acetylcholine. We also here have a sodium-potassium pump. And this is called the sarcolemma, as we talked about earlier. Shoots potassium out, puts sodium in, and what that does is that starts another action potential, sending a signal down here, which as it sends that signal down there, it pushes this potassium out, and also creates a gradient here. But we have these two little channels here. It's called the DHP and this is called the iodine. Okay, and in the ESR, we already have calcium, but it is used. And it is used over here in a sarcomere. So calcium will go, okay, calcium will go through this channel. This is another ryanide. And this will go through and it will bind to that, I'm sorry, I'm spacing on it. I'll just have to look. To the troponin. It'll bind to the troponin and create that conformational shift. And what it does after it binds is it will just be deposited back out here. And then we have these pumps that will pump it right back in. These are called the circuit pumps. Not all of it will be pumped back into the SR. Some will come through this voltage gated calcium channel. There was supposed to be one there. And so that is more or less how we kind of start that process. I will now teach you about how the process of this myosin head connecting. So we have this. I'm going to move this right here. Okay, we call this the cross bridge cycle. I'm just going to draw out a bunch of these. By bunch, I mean 4. There's arrows between them. Okay, so we're going to start. We have ADP and a phosphate. So once again, this is your myosin. And then this is the actin. So what we're going to add here is we're going to add calcium. What calcium is going to do is it is going to help us perform that conformational shift. And we are going to bind right to that myosin. DP. Here is what we call our power stroke phase, in which we're going to lose that phosphate that's attached right there, and we're going to lose the ADP. That's going to leave us with, this binding to the actin with no ADP, but it's going to move like this, kind of at an acute angle. This is going to cause, it's going to be called half cocked. This is full cocked, kind of like a gun. You have the hammer on a gun. It's pulled back, it's cocked, and this is half cocked. It's not there. What we're going to do here is we're going to add ATP. And ATP is going to bind to the top there. And actually, just kidding. So as we add that ATP, it's going to break that bond between the myosin and the actin. It's going to leave us down like that. This is going to be called hydrolysis. And it's going to make, it's going to open up that, it's going to open it up because what it's going to do is it's going to break the bond between ATP and one of its phosphates, and it's going to phosphorylate our myosin. So that's our cross bridge cycle. So skeletal muscle go around and around like that. We're going to talk a little bit about where this ATP comes from and the benefits of each. So our first source of ATP is our cytosolic cytoplasmic, I'm sorry, ATP. And this actually only lasts 1 to 5 seconds. It's not very good. Our second source is creatine phosphate. And you may have heard of creatine. Creatine is used a lot. It's a supplement for people in the gym. What it does is it just gives that extra couple of seconds to lift weights. And what it does is it floods your muscles with water. That's actually why you do see some results in the gym. Next up is glycolysis. Glycolysis is an excellent way to break down glucose into ATP. It will give you 60 seconds of usage, but most effectively, so all of these are anaerobic. Means we don't use oxygen. Aerobic respiration is by far our most used or our most effective. We can use it for hours. The only thing is it does use oxygen. So, and now we're going to talk about the different types of muscles. This is something I drew up earlier. We're going to go through each one. Myosin activity in type 1. So type 1, it's oxidative, uses oxygen, but they work differently. Type 2A is as well oxidative, and type 2X is glycolytic, meaning it does not use oxygen. So its myosin activity in type 1 is slow, type 2A is fast, and type 2X is as well fast. The diameter of type 1 are fairly small. We have medium and then large. The duration of the contraction is long. It's short for type 2s. The circuit pump, we just talked about that, pumps calcium back into the cell. It's very slow for type 1. It's medium for type 2, and it's super fast for type 2X. But with that being said, with fatigue, type 1 are very resistant to fatigue. Type 2A is kind of in a medium, and then type 2X is very easily fatigued. And we're going to use that energy of oxidative. That one has both, can use both glycolytic and oxidative. And then type 2X is glycolytic once again. So our capillary density, they're highly innervated by capillaries in type 1. There's kind of a medium amount, and then there's a very low amount in type 2X. The color as well correlates, can be red, and white due to the amount of blood flow that it gets. The mitochondria is high in type 1, very medium in type 2, and low in type 2X. So something that correlates is this type 1. Everybody has a different amount of the types of muscles, but females typically have a higher amount of type 1. Males typically have a higher amount of type 2X, meaning that females can typically have a little bit more stamina. They're a little bit more resistant to fatigue, while men typically are more able to do more fast, energetic movements, but are not necessarily able to be resistant to fatigue as much as women are. And this is definitely something that can be trained and learned through time, but it's not always just natural. Some people have it more natural than others. So now we're going to talk a little bit about smooth muscle. So this cycle that we just talked about, the cross bridge cycle, actually just going to copy it over, and we are going to adjust it. So there's two types of smooth muscle. So smooth muscle, what's the difference if you don't know? Smooth muscle is found in your organs mainly. This uses the same thing. The only difference in smooth muscle is we don't have troponin found in it. Oh, I'm gonna leave that. Oh. And this is going to be called phasic. So phasic is going to be a high energy. And then tonic is going to be a lower energy. So we're going to start off the same way. There will be a lot of differences in here. We're going to add an ATP with the calcium. So this is the same ADP and a phosphate. We have calcium, ATP, and then we're also going to use an enzyme called MLC, okay? That stands for kinase. The K is kinase. If you've taken biochem, that typically means that we are going to add a phosphate group. So that's what we do. We use that ATP and add a phosphate. We still have this power stroke, and we're going to remove that phosphate and that ADP. And that's going to leave us here. Still have a phosphate group attached. And then we are going to add an ATP. I don't like the way I drew that, so I'm going to erase it. There's still a phosphate group attached. And then here, in hydrolysis, we're going to use another enzyme. This is called MLCP. That's for phosphatase. What it usually does is it removes a phosphate. So there's actually two cycles we can use. We can go back up to the top, or there's also the ability we can just go right back over to this same pathway using our hydrolysis. And so this is used in most of our organs. For here in the tonic, we have a little bit of a different situation going on. We're still going to use ATP and this MLCK to add that phosphate group right here. The power strokes phase is a little bit different. We're removing that phosphate originally and the ADP. Afterwards, we're going to have MLCP come in. And we know when that happens, we're going to remove that phosphate group. That's actually just going to leave us right here. This is the exact same. We are going to try adding this ATP, but instead of it actually happening, it is going to stay up like that. And this ATP is going to try coming in and is going to be rejected. It kind of goes back and forth. And so we call this the latch state. I like to think of it like a latch on a gate where it just kind of locks it in place. So this is actually used a lot in our sphincters in our body, or other muscles that we want to just stay contracted for a long period of time. As you think about it, you don't want any of the sphincters in your body, especially your internal anal sphincter, sphincters such as that, you don't want them just leaking. You want that muscle to stay contracted and stay tight, and so it'll stay bound. That myosin will stay bound to the actin. There is a little difference in the way that this works in smooth muscle versus skeletal muscle. Skeletal muscle, we kind of have this thing going on where we bind to this actin. In smooth muscle, we actually have these two sides that will kind of slide past each other as they bind. So it will help us to understand that as this smooth muscle contracts, it can contract smaller and tighter than skeletal muscle, but it works a little bit differently. So it uses this phasic and the tonic pathways to do that. Next and lastly, we're going to talk about reflexes. So reflexes are important in muscles. So I'm going to draw a hand. This happens to me frequently. Besides, my hand doesn't look like an alien hand. Say I'm cooking food, be chopping up some carrots and have my knife. And oops, cut myself. So there's going to be a reaction that happens here in my spinal cord. Oh. The spinal cord. My hand is going to send a reaction up to my spinal cord. And actually, before it ever goes up to the brain, what we'll do is it'll synapse right here and come over and go right back to my hand. And what that's going to do is that's going to force me to move my hand. I'll move my hand back. And so the process of this is we first have our receptor in the hand that feels the stimulus. It's going to send that message back up to the sensory nerve. So we call this the afferent pathway. And then this is called the efferent pathway. So our control center, right where it synapses into our motor neuron, causing me to move my hand back, and into the effector, which is causing that motion for me to move my hand. So I'm going to copy this pathway right over, and we're going to talk about it in a little bit of a different sense. Okay, so in our skeletal muscle, all right, that works. Our skeletal muscle, we have this thing. I'm sure it's going to look weird when I draw it. It kind of looks like this piece of candy. What it is it is called a spindle apparatus. And the spindle apparatus, it has some sensory components. And then we have some innervation here for these two muscle pathways. One is called the alpha motor neuron, and this one is the gamma motor neuron. So I'm going to draw a leg here. Bear with me, I'm not the best at drawing. So we have head of our femur coming out. And those were not supposed to be like that. That's okay. Patella. Tib, fib. Okay, and then all of this is muscles. We have a lot of muscles coming down. Okay, so when we're at the doctor, he uses his weird hammer to test our reflexes. I'm going to tell you why. Or what happens when it does. That looks like a butcher's knife, but and that would have a little bit different effect, but we'll roll with it. Okay, So the doctor, he hits our patellar ligament, causing our muscle to contract, which goes up and it synapses here, sends a signal to the brain. The brain. And this will actually synapse a little bit differently than we drew here. Well, it will. It will do that. It will also end early. And we have these two pathways coming out, both going back to the muscle. I don't know why I did that one. Okay, this is called, this little yellow or orange portion is called our interneuron. And so this will synapse, it'll send a positive signal down, but what our interneuron will do is it'll send a negative signal down. So these two are actually running to different muscles. One to the glutes and the other, one to the hamstrings and the other to the quadriceps, which the glutes would be a little farther down. But so when we have this signal, when the doctor taps our knee, what's going to happen is it's going to send that signal down. So it's going to go and cause our muscle fibers, our spindles to contract. It's going to send a sensory neuron down through an action potential, and it's going to synapse right there, as we talked about. It's going to synapse with the alpha motor neuron of the quadriceps. Okay, and it's also going to synapse. It synapse with the interneuron, which causes it not to contract, which is really good. You don't want your leg to contract both on the front and back side, both at the same time. I feel like that's a pretty bad thing for your leg to just not move. What'll actually happen in this, it'll hurt you quite a bit. So that will cause the alpha motor for the quads to shorten and contract. Cause the alpha motor for the hamstrings to relax. Forcing your leg to move. I'll try a little move as this muscle shortens. The front of your leg will go out like that. So next, what we're going to talk about is a little bit different of a pathway, which has a lot to do with this, and it's very useful, very, very useful. It's a blessing to have one. So we call this our Golgi sense. What it does is, as we know, right here we have a tendon. This tendon connects to our muscles. Tendons connect bone and muscle. They're how we hold on. So our Golgi sense, what it'll do is it'll tell this sensory neuron and say, hey, this tendon is getting pretty striated. It is getting pretty tensed up, and we need to do something about it. So it sends out a message to the brain, and it works in this complete opposite way of how we just had it. So we will have an interneuron right here going to the quads. We also have one going directly to the hamstrings. What it's going to do is it's going to tell the quads, hey, chill out, relax. It's going to tell the hamstrings that it can tighten to release the tension off of those tendons up on top. And so we're going to go through this. List it out again. Golgi sense. Okay, we have our Golgi sense reflex sense. Sends a message to our sensory neurons. It sends a synapse down. As we synapse, it's going to cause the alpha motor of the hamstrings to contract, forcing our quadriceps to relax. So this is actually a very important system, and we can learn about it a little bit more as we look at examples in life. So there are, this actually happens quite a bit in athletics and just in everyday life. So this Golgi reflex, it'll tell our body to chill out, it'll be okay. All we got to do is relax our muscles. But what can happen is our sympathetic nervous system can overtake that sense, and then it'll just tell us to just keep staying with it. Just stay firm. We're in a life or death situation. And what actually ends up happening is, because that Golgi sense doesn't work, we end up tearing some tendons. So you hear that a lot about athletes going and tearing tendons in their legs, having these injuries. And that's all from that Golgi reflex sense not functioning as it's supposed to. Okay, so that's been this lesson today. It's been a lot of information. Thanks for sticking around.